The GAMMALN function within Excel allows us to calculate the natural logarithm of the gamma function. This is something that could be useful in math, statistics, or quantum mechanics. The function itself is quite straightforward. So we write equal sign GAMMALN. We open the parentheses and we only have one argument, being the x. So we supply a number to the GAMMALN function. I close the parentheses and you press enter. We can see that for -5 we get a calculation error. Now let's fill this out. And we can see that for all the negative numbers, including 0, we receive calculation errors, whereas for the positive numbers, we are actually getting some results. Now, what does this mean, this GAMMALN function, and where does it come from? Now, the GAMMALN function finds its basis in the factorial function. And so taking a factorial of a number is something you might be familiar with. So generally we write this as x exclamation mark. And so to take the factorial of a number, we also can use an Excel function for this, which is called the fact function. Once again, it only takes one argument, being the number. So I put in the number and I pull this through. Now, once again, you can see that for all negative numbers, we once again get a calculation error, but we do get some results for 0. Now, how is the factorial function calculated? Well, we take a number and then we multiply this number with all previous whole numbers that came before it. So how this 24 was calculated was by doing 4 times 3 times 2 times 1. As you can see, that equals 24. And so the 120 was calculated by doing 5 times 4 times 3 times 2 times 1. Now, one thing you can see is that with the fact function in Excel, we are actually getting result for decimal numbers. This is something that is normally not allowed in math, as we cannot take a factorial of a number that has a decimal. So Excel is being a bit liberal here, and so he's rounding down this 4.5 to a 4 and then taking the factorial of that whole number, resulting in 24. Now what the gamma function does is subtracting 1 from x and then taking the factorial of that. So it would look like this, 1 minus x and taking the factorial of that. So we could also write this in Excel as fact and then taking the x minus 1 and press enter. Once again, we get a calculation error. And as you can see, our values have shifted 1 down, obviously because we subtracted 1. Now, the beauty of the gamma function is it does not only subtract 1 from x. Through analytical continuation, we are filling out the dots in between the whole numbers that we're getting. So what the result would be between 2 and 3, what the result would be between 0 and 1, and also between -3 and -2. We do this in a complex plane, and the explanation is a complex integral, which is not the scope of this video. But so to take the gamma function, we can use an Excel function for this as well, which is called the gamma function. The gamma function takes in one argument, a number, and then returns the corresponding value of the gamma function. Now, if we pull this through, you can see that for some negative numbers, we are actually getting results. Now, the gamma function is not defined for whole negative numbers. So only for decimal negative numbers, you will get a solution. That's because there are asymptotes at those whole negative numbers. One thing you can also notice is that the results match between the gamma function results and the x minus 1 factorial results only for whole numbers. So for 1, 2, 3, 4, etc. But it does not match for those decimal numbers. So 3.5, well, the factorial function is returning 2, whereas the gamma function is returning 3.3. So what the gamma function does, it is interpolating and seeing what the result would be if we took a value between 3 and 4. Which is something we could not do with the regular factorial function, even though Excel is still returning us results for these decimal numbers. So what happens then? Well, we take the natural logarithm, or the ln, of whatever was returned by this gamma function. So let's take the natural logarithm of this gamma function. For this, we can use the ln function. And so we supply it a number, so whatever was being returned by the gamma function, and we pull this down. Now, a logarithm, you can only take that from negative numbers. So only there where the gamma function supplies us a positive number, we are able to take the natural logarithm. Now, the natural logarithm comes of course from a regular logarithm. Now, what logarithms allow us to do is to find the exponent to which we have to bring a number to a power to get a certain result. So let me explain. If you take 2 to the power of 3, we get 8 because 2 times 2 times 2 is 8, right? That's what's going on. We're multiplying 2 3 times with itself. Now, what we would like to find is to which power we have to bring 2 to get a 3. In other words, how many times do we need to multiply the number 2 to end up with 8? And so for this, we can use the log function within Excel. So we take the log of 8 and it's a log 2, so it has base 2. So that's the second argument. If I close the parentheses, you can see we get 3. So in other words, what this means is that we have to take 2 to the power of 3 to get 8. So this logarithm allows us to find an unknown exponent. Now, what the natural function is, it uses Euler's number as the base. Now, there's also a function we can use within Excel to get Euler's number. So that would be the exp function. And so if we simply input 1 in the exp function, we will get Euler's number, or E. So it is 2.71828, etc. Just like pi, this continues indefinitely. Now what we could do is take Euler's number and bring this to a certain power. So let's write exp1 to get Euler's number and then bring this to the power of 3. Now what we would like to find is the exponent on E needed to end up at 20.80855. So how we do this is we take a log, just like before. The number is a 20.0855. And the base, well, that's Euler's number, so exponent of 1. We press enter, and as you can see, we end up with 3, which was indeed the power to which we brought Euler's number. Now, there's a simpler way to do this, and that's using the ln function. And all this does is take the natural logarithm, just like we did before here. So we use a logarithm with the base of e. Well, that's exactly the same as using an ln function. So we use a ln on this 20.08, press enter, and you can see we end up with the same tree. So that's what's going on with this ln function. Now, one thing you might have noticed is that when we compare the results of having taken the natural logarithm of the gamma function and compare it to what was received by the GAMMALN function, it is not exactly the same. So if you take a look at the strictly positive numbers, you can see that it does match. So those actually make sense. But then if we take a look at negative numbers, you can see it does not match. The GAMMALN function always returns an error, whereas actually if we do this the mathematical way, you could actually get results for negative values using the GAMMALN function. So this is something to take into consideration whenever you're working with the GAMMALN function, that it will not return correct results when using the GAMMALN function on negative numbers.